Hello, today we're going to review Unit 8 on acids and bases for the AP Chemistry exam. We're going to do some free response and multiple choice questions. Okay, so we have two halogen oxyacids in the table. Which of the two acids is stronger, HOCl or HOBr, and justify your answer in terms of Ka. So HOCl will be stronger because its Ka value is larger. Notice the exponents. So the stronger the acid, the larger its Ka value because it dissociates more. And that was just 1 point. For part II, draw a complete Lewis electron dot diagram for the acid that you identified in part A. So you'll have the oxygen in the middle and the hydrogen and the chlorine are on the outside. The oxygen and the chlorine have lone pairs. If you used dots instead of the lines for the bonds, you could have, that's fine. The Lewis dot diagram would look like this, and that's fine too. Either way is okay. That one was worth 2 points. One for getting the correct orientation of the atoms. The oxygen needs to be in the center. Because hydrogen and chlorine can only form the one bond with the oxygen, one bond each, and then another point for getting the correct lone pairs. So each atom needs to have a full valence shell. Hydrogen only needs 2 electrons for the full valence shell. Oxygen and chlorine both need 8 for the full valence shell. So the oxygen needs 2 lone pairs and chlorine needs 3 lone pairs. Okay, so the next one, hypoiodous acid has the formula HOI. Predict whether HOI is stronger or weaker than the acid and justify your prediction in terms of chemical bonding. So HOI will be weaker than either of those. And the reason for that is because of the electronegativity difference. So notice how these are all halogens in the same group, and if you put them in order, chlorine is the highest up on the periodic table and iodine is the lowest. Chlorine has a greater electronegativity than iodine does. So let me go ahead and draw this out again. It's going to have a very similar structure for the HOI, but chlorine has a greater electronegativity, so it's going to pull the electrons closer to it, leaving the hydrogen free to leave more frequently. Iodine has a lower electronegativity than chlorine. Because it's lower electronegativity, the electrons are free to move more towards the hydrogen, which holds on the hydrogen tighter. So that's where you're getting from. Whenever it talks about the strength of acids or bases, really acids are more common, but you always want to look at terms of electronegativity. The ones with the higher electronegativity are going to have stronger acids typically because they're pulling the electrons away from the hydrogen, leaving the hydrogen free to move off as an ion. Write the equation for the reaction that occurs between hypochlorous acid and water. So it's an acid. That means the water is going to act as a base. So you'll be left with OCl negative and H3O plus. And this is your conjugate base, conjugate acid. 1 point, all or nothing. Okay, so if we continue on with this free response question, we have the hypochlorite reacting with water. This is acting as a base. This must be acting as an acid because they're transferring electrons. This is the conjugate acid and conjugate base. When we write the equilibrium constant expression, then I know it's a Kb expression because it's a base in water. So my products go on the top, the HOCl and the OH negative, and the OCl negative on the bottom. And that was 1 point. Now for II, calculate the value of the equilibrium constant for the hydrolysis reaction. So they wanted you to notice that OCl negative is the conjugate pair of HOCl. And we know HOCl has a Ka value of 2.9 times 10 to the negative 8. And that was in our data table. Since I know that, I can find the Kb because Ka times Kb is equal to Kw, which is 1 times 10 to the negative 14th at 298 Kelvin. But that only works when they're conjugates. So I'm going to go ahead and divide 1 times 10 to the negative 14 divided by the 2.9 times 10 to the negative 8th. I don't know why I wrote 18th. And I'll get my Kb value is 3.45 times 10 to the negative 7 for that OCl negative. Now I need to calculate the value of the OH negative concentration in the 1.2 molar sodium hypochlorite solution. I can use an ice table. OCl negative plus water yields that HOCl plus OH negative. I have a 1.2 molar solution here. The water doesn't matter. We have our ice table. I don't have any of this stuff to begin with, so I know that this will decrease by X, and this side will increase by X for each because it's all a 1-to-1-to-1 relationship. So at equilibrium, this will be 1.2 minus X. This will be X, and this will be X. Now I can plug those values back into my equilibrium expression, my Kb expression that I wrote in part I. So the Kb I found was 3.45 times 10 to the negative 7th. This will be X squared on the top and a 1.2 minus X on the bottom. If you solve for X, you get 6.43 times 10 to the negative 4th, and that's equal to X, which is equal to our hydroxide ion concentration. So there's my final answer there. You could have also assumed that X was very small and solved it that way, so ignoring the X on the bottom. You might have gotten a slightly different answer, but within significant figures, so you can do it that way as well. Now for part D here, buffer solution is prepared by dissolving some of that sodium hypochlorite in a solution of the hypochlorous acid. The pH of the buffer solution is determined to be 6.48. Calculate the value of H3O plus. So pH, you can do H3O plus is equal to 10 to the negative pH. So that makes this calculation really simple. You just 10 to the negative 6.48. You get that the H3O plus concentration is 3.31 times 10 to the negative 7. And then it says indicate which of the acid or the conjugate base is present at the higher concentration in the buffer solution and support your answer with a calculation. I think that the easiest way to solve this is probably to find the pKa. Okay, so if you take the negative log of the Ka value for this acid, which is 2.9 times 10 to the negative 8, we get the pKa, which is 7.54. So my pKa is larger than the pH, which is 6.48. So it's more acidic than it would be if they were equal concentrations. When the pH and the pKa are equal, then you'll know that these two have the same concentration. Well, my pH is lower, so that means it's more acidic. So I will have more of the HOCl present. And that one was just 1 point for I and 1 point for II, but you had to do both. You had to calculate the pKa and compare it to the pH to explain then that you must have more acid in the solution. Okay, this is a different free response question. I wanted to do one with titrations as well. So we have a 0.1 molar hydrochloric acid solution, 0.1 molar sodium hydroxide solution, a 40 milliliter sample of one of them is added to a beaker and then titrated with the other one. A pH electrode is used to obtain the data. Identify the solution that was initially added. It was the HCl because it starts at a low pH. And then on the titration curve, circle the point that corresponds to the equivalence point. The equivalence point will be right here, right at 40 at a pH of 7 because you have a strong acid titrated with a strong base. At equivalence point, how many moles of titrant have been added? So the titrant is the one that's being added. So that is the sodium hydroxide. And we used 40 milliliters of it to reach equivalence point, or 0.04 liters, and it was a 0.1 molar solution, and molarity times liters will give you moles, so 0.004 moles of the NaOH at equivalence point. Each of those is just 1 point each. Okay, for part D, the same titration is to be performed again, this time using an indicator, and use the information in the table to select the best indicator and explain your choice. So you need to look at where the color change is happening in the pH range. So methyl violet is in the 0 to 1.6 range, so it's changing right here, nowhere near the equivalence point. Methyl red changes in the 4 to 6 range, which is right there. And alizarin yellow changes in the 10 to 12 range. So in this case, pH 4 to 6 is going to be our best choice, so methyl red. And that's because even though it's before the actual equivalence point of a pH of 7, we can see that there's no change in volume from the equivalence point in that pH range of 4 to 6. So methyl red is going to be your best choice for that one because of the information on this titration curve. And this one was 2 points, one for getting the correct indicator and one for the correct explanation, stating that there was no significant change in volume during the pH change of 4 to 6. So you could still tell the correct volume for equivalence point. Now for part E, what is the difference between the equivalence point and the end point? This was also a 2-point question. So equivalence point is where the moles of the acid and the base are stoichiometrically equivalent. And that's true for any titration. It doesn't have to just be acids and bases. It's where the moles of both reactants are canceling each other out perfectly. That's the equivalence point. And then for the end point, that is where the indicator is changing color, which we want to try to be as close to the equivalence point as possible, but it might not be, and depending on the indicator that you choose. And so this is actually one of those sources of error that you can talk about if a question were to ask about that. If the endpoint occurs past the equivalence point, then that additional volume of titrant was going to affect your final calculation. Okay, so it says the kW for water at 0 degrees Celsius is 1 times 10 to the negative 15. Well, that's different. We're used to kW being 1 times 10 to the negative 14, and that's because we're typically measuring it at 25 degrees Celsius. So when the temperature changes, all of our standard knowledge about pH, like the maximum being 14 and neutral being 7, like all of that changes. So in this case, it says, what is the pH of water at 0 degrees Celsius? Well, kW is always going to be equal to the hydroxide ion concentration times the hydronium ion concentration, or hydrogen ion concentration. And those are equal because it is pure water, right? It's water, so those are equal. So I can say that kW is equal to x squared. And then I can take the square root of both of those things to find the value of x. So I get 3.16 times 10 to the negative 8 equals x. And then I can take the negative log of this value to get to the pOH. So negative log of that answer is 7.5. So my pOH is 7.5. But I will tell you about this question. That means the pH is also 7.5 because x is the same for both of these. It just means that 7.5 is neutral when the temperature is 0. So just be careful with that, okay? Okay, so how can a 100 milliliter of sodium hydroxide solution with a pH of 13 be converted to a sodium hydroxide solution with a pH of 12? Okay, so I'm going to go ahead and do this the mathy way because you guys are allowed to use calculators now on the multiple choice. So if I have a pH of 13, that means my pOH is 1, and that means my OH concentration is 1 times 10 to the negative 1, or 0.1 molar. I have 0.1 liters of sodium hydroxide, so that means I have 0.01 moles present, 0.01 moles. Now, if I want to get a pH of 12, that means my pOH will be 2, and my OH concentration will be 1 times 10 to the negative 2, or 0.01 molar. if I still have those 0.01 moles. So molarity is moles per liter, 0.01 moles. I need to find the amount of liters, total liters, that would make this true. And so X would be 1. I need 1 liter total of solution to make it to a pH of 12. So C is the correct answer to get that. You could also have kind of thought through it, because we have 100 milliliters at a pH of 13. I need to dilute it to get the pH to decrease, to get closer to neutral. And I need to dilute it 1 pH unit. 1 pH unit is equal to 1 order of magnitude. So instead of 100 milliliters, we need 1,000 milliliters now, which is 1 liter. So either way you figured this question out, it's fine. Okay, so this is an interesting one because it has, the 3 different acid forms for phosphoric acid, and the hydrogens leave sequentially, and they give us the Ka values for each of those sequential deprotonations. Now, a buffer of the pH of 9 can best be made by using what? You want a buffer where your pH is very close to the pKa. So let's go ahead and find our pKa values for each of these. So when I took the negative log of each of those, I got 2.15, I got 7.09, and I got 12.3. So we don't want only the H2PO4 present. Even though this will dissociate, it won't form a buffer system there. For this first answer choice, those are a conjugate pair, but it's based off of the pKa of the acid, which is this one in this case, in this scenario. This one's acting as the acid, and the other one is the base. So it would be too far away from the desired pH. The next option is not a good choice at all because of the 2 hydrogen difference present there. Also, PO4 2 negative just isn't an ion. It's PO4 negative 3. The next answer choice is probably the best one. Actually, both of these you might be able to get to pH of 9, but of those 2 answers, the H2PO4 pKa is just a little bit closer to a pH of 9. You would need more of the conjugate base present than the acid to get it the pH higher than the pKa. But I think D is the best option here because it is because the pKa of the acid is closest to the desired pH. Okay, so here's a really straightforward acid-base question. You definitely need to know how to do this one. When you're dealing with a weak acid, that weak acid is going to partially dissociate into hydrogen ions and cyanide ions. These hydrogens can attach to water molecules to form hydronium, but a lot of times we will shorthand and not write out hydronium. Now, that means our Ka expression is going to be the hydrogen ion concentration times the cyanide time all over the HCN concentration. And if I were to, let me go ahead and write out this reaction again. If I were to have this present at equilibrium, I can use an ice chart. Okay, I have 0.05 molar HCN to begin with and none of the hydrogen or cyanide. We assume that the instant that you make that solution, none of it has dissociated yet, but some of it will. So this will go down by x, and this will increase by x using the coefficients. So we have 0.05 minus x, x and x. And the Ka, let's go ahead and plug into the equilibrium expression. We have 5 times 10 to the negative 10 is equal to x squared, because they're both x on the top, over the 0.05 minus x. Now you could use a solver function or graphing function in your calculator to find x, but considering that this value for Ka is so small, you can probably ignore x here and have it be the same answer with correct significant figures. So let's solve it. And you get, either way, you get 5.0 times 10 to the negative 6th is your value for x. Now it's asking for the H plus ion concentration, which is just x, so it is D. A very frequent follow-up question to this is then, what is the pH of the solution? You would just take the negative log of your H plus concentration. Okay, nationic equations. Nitrous acid is a weak acid, so it's HNO2. It does not significantly dissociate. It does dissociate, but not enough for us to split it apart into ions in a nationic equation. Sodium hydroxide is a strong base, so I'm going to go ahead and split that up into sodium ions and hydroxide ions. Now, in solution, you're going to form water, and the sodium will attach to the nitrite. But group 1 metal salts are completely soluble, so you'll wind up with the sodium separate from the NO2 minus, and the sodium becomes a spectator ion. So I wind up with that HNO2 reacting with the hydroxide ions to form water and my nitrite ions on the product side. So E is the best answer choice.